Welcome. Today we're going to be looking at the notes worksheet entitled Polar Equations. And so this lesson represents an extension of yesterday's development of the polar coordinate system. And if you remember correctly, yesterday we took more of a point perspective on the coordinate system. And so today we're going to transition a little bit and take a look at some real basic polar equations there. You do need a graphing calculator for this particular lesson, so please have one available. So let's do just sort of a review problem here to start it out. This would be the example one you see on your paper. And then we'll throw a couple review ideas and then really just come up with some of the equations there. We'll kind of go back and forth. Rectangular form, of course, if you remember everybody. That was with x and y. And now polar form with r and theta. So let's go for it. Example one, it says plot 2, 240 degrees and come up with 5 ordered pairs for this point. Okay, so let's first of all do the 240 here. And so remember what I talked about yesterday is do the theta first. I think that's really helpful to do theta first. So here's the 240 terminal side if I rotate around like this. So here's 240. And a positive r value keeps us there. And so as a result, I'm seeing that point right there. And as a matter of fact, I'm going to go ahead and draw sort of just a dotted line going to it. Just something like that. So remember in this case, in fact, I'm just also thinking out loud with this. I'm going to go ahead and do sort of this piece. That would be 240 degrees. And of course, a positive r keeps us on that terminal side. All right, now, here's what I would ask you to do. Pause the video and try to come up with at least 3. We're going to try to do 5 up here eventually. But try to come up with at least 3 other ways to represent that point. Use positive r's, negative r's, positive thetas, negative thetas, totally your call. All right, well let's see what we want to do here. I guess I'm going to do a couple initially. How about this? I'm just kind of thinking about this piece right here. I'm going to do a couple with a positive r, just kind of sort of thinking about that. So, and again, this is just my thought on this. If you want to go a different way, that's perfectly fine. And remember the premise would be this, everybody. If r is positive, then what we want to do is rotate to the terminal side directly to the point. So what I mean by that is, again, there are an infinite number of ways to do that. I did this 240 degrees. That works fine. What if I went clockwise from here to here? That would be a way to go ahead and rotate directly to that terminal side. Clockwise, of course, is a negative angle measure, as we all know. And so what would be the rotation from here to here? Well, I'm seeing this as 90 degrees and then another 30. So I'm seeing this as 120 degrees clockwise. So that would be a way to represent that point, to locate that point on the polar coordinate plane. So that's one. Okay, now let's just come up with another. Well, again, here's my initial side, everybody. Let's do a counterclockwise rotation here. So I went 240 here. What if I went once around first and then went another 240? So that would be 360, another 240, and 360 and 240 added together would be 600 degrees. Perfect. That would be another way to do that. Going more than one rotation around and getting to our terminal side. Just kind of thinking again, how about I do it clockwise and same situation. So here we go. I'm going to go 360 clockwise and another 120 degrees. So again, follow my pen here. Once around and then another 120 there. And if I do that, it looks like I would get negative 480. So that would be 360 clockwise and then the 120. 360 and 120 make the 480. Good. And that's, just scratching the surface. Obviously, I can keep going around and around and around as many times, clockwise or counterclockwise. If I end up on this terminal side with that point, r is going to be positive. Okay, well, let's do just a couple more here. How about what happens when I have a negative r value? So remember here, everybody, in this case, if r is negative, I'm not going to rotate directly to this side. I'm going to rotate to across, so through the pole, basically, 180 degrees around. So I guess the thought is, in this case, how can I rotate from here to this terminal side? Because then the negative r makes me go right on through and land on this point. So that's what we talked about yesterday. And I guess there are different ways to go ahead and rotate here. I'm just going to take the most direct route right here to here. And so this seems to be 60 degrees in a counterclockwise fashion. So that would be one right there, -2 and 60 degrees. Because I would go to 60 degrees, everybody, but r is negative, so I go through the pole and I land right here. Okay, and then how about a -r and a negative theta? So that would be going to this terminal side and rotating clockwise to get there. So what would be that angle measure from there to there? And I think that angle measure looks to be -300 if I'm playing that out right. Here would be 270 and another 30 for 300. And so a -r, negative theta, and let's see if I gave you that particular ordered pair, you would do 300 degrees clockwise, get you there, but a -r would go through the pole and 2 units through the pole, and there it is. So you can see really the sky's the limit in terms of coming up with ordered pairs for any particular point. And we talked about that on the previous notes worksheet. That is the fundamental difference between the two systems. An infinite number of pairs for each and every point. All right, good. Hope that clarifies a few things. If not, please ask questions about it. But it's almost like there's a little ... on this as this can keep going and going and going. Alrighty, so the review from yesterday, everybody, is just really the idea of polar to rectangular, rectangular to polar. As I said, we saw in a point context, and now what we want to do is see it in an equation context. So everyone, if you would, excuse me, on this blank right here, remember, if you have r and theta, it's easy to convert into x. So r cosine theta is x. And if you have r and theta, it's easy to convert to y, r sine theta. And by the way, we will be seeing this type of math come up in at least 2 other topics of discussion this semester. So keep this in mind there. X, or the horizontal, I should say, really. The horizontal is r cosine theta, and here y. And really the vertical, of course, is r sine theta. So please keep that in the back of your mind as we move forward with this. Let's see, we kind of had a couple other things really go in reverse, rectangular to polar. This was one right here. And then I'm just going to put this off to the side because you see this come up with equations. So x squared and y squared would be r squared. So either way there, obviously they mean the exact same thing. And then, you know, just sort of this piece right here, we've talked about having x and y and getting theta. And then, so just remember that piece right there. That's what we'll primarily use if we see it today. Just one thing to note, though, and I'm just going to do this. So when appropriate, don't forget, this is really more with yesterday's lesson. So when appropriate, add the 180 degrees. Maybe just put that very lightly off to the side. That's not something we're going to hammer home today. Because again, that's more with the points, not the equations. So if you remember correctly, when the horizontal part is negative, and again, keep that in mind as we'll see that a couple different times this semester. When the horizontal is negative, we do have to add 180 degrees. And that's what we saw in the previous notes worksheet. Okay, very good. So as I said, we'll go ahead and just graph some here a little bit, see what you guys think. We'll use a graphing calculator to help us out a little as well. So as I said, have that available. We're going to see a new mode on your calculator in just a few minutes. Okay, everyone, so on your paper it says a polar equation. So here's what I see right here. Polar equation is an equation whose variables are r and theta. So remember, this is just a different system to represent a relationship in 2 variable quantities. In this case, the representation of those quantities is in r and theta. You would sort of consider theta the independent variable, for lack of a better description, and r the dependent variable, again, for lack of a better description. And so what we're going to do is write this in what we would call our explicit form, r equals. In rectangular form, of course, everybody, that would be y equals, y in terms of x. And in this case, it's going to be r in terms of theta. So we're going to start out with a couple very, very basic ones here, and then kind of get the ball rolling. We'll do some conversions off to the side as best as possible, and see where it leads us. So first of all, let's see what r equals 2 looks like. It's kind of a nice simplistic equation here. What graphical pattern would it make on the coordinate plane? So how about this? Just if you get a chance, find any point on the polar coordinate system where the r value is 2. So I'm going to go ahead and find one. Here's a value where r is 2. 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 That's all it's saying, r is 2. And I keep doing this, r is 2, etc., etc. If I was to do the infinite number of points where the r value is 2, what would you end up getting? Well, I see it as just a nice perfect circle there. And so you see just a very, very nice simplistic way to represent a circle on the coordinate plane. And it makes pretty good sense, right? Radius is 2. And there it is, guys. Look, radius is 2 units. And by definition, all the values that have a radius of 2 would form a circle on the coordinate plane. Cool. We're going to check that out on the graphing calculator momentarily. For right now, let's go ahead and see if we can convert this. I'm going to try to find some room right here. So let's go ahead and just write that in somewhere. You might be able to do it down below. I don't have any room on this particular board, but I'll figure it out. And here's what I'm thinking. We want to convert this to x's and y's. And so a couple different things that you can do here. I see two different paths to this, by the way. I'm thinking either we can square first, which is probably the path I'm going to take, or I can convert r right away because, let me just go to my other board for a second. Don't we know what r is, everybody? Isn't r just this? And wouldn't that put us in x's and y's as opposed to r? And that's the idea, everybody. When I say convert, we want to get rid of all the r's and thetas and convert it to x's and y's. Well, if it's okay with you, what I'm going to do first, as a matter of fact, is square both sides. So square the r, I get r squared. Square the 2, and I get 4. Sort of typically how you would see this one run. And then everybody, here's the situation at hand here. Obviously, the 4 stays as is, but what I'm looking for here is a way to convert r squared. And again, I'm going to just keep going board to board here. Look at what r squared is, everybody. Using the Pythagorean theorem, r squared is this quantity right here. And when I change r squared to this, everybody, haven't I, in essence, changed to rectangular form? Sure. And so here's what I have. That should be an x squared, y squared, and then equals 4. And that's exactly it. So you see two different ways to represent a circle on the coordinate plane. Again, it's all it is. It's just two different representations. In some cases, some graphical patterns, rectangular form happens to be a little easier. I would say that not here. In some ways, I would say polar form is definitely an easier mathematical representation. And in this case, I would say polar is by far easier. Writing this as an equation is quite a bit simpler than writing this as an equation. But if you remember from first semester doing conic sections, this is a circle on the coordinate plane, center at the origin, and a radius of 2 units. Remember, this is r squared over here. So it all comes together pretty nicely. So anyway, this is the rectangular version of this right here. Two different forms to model a graphical pattern on the coordinate plane. That's all. Well, let's bring the calculator up for just a second and kind of see this for the first time. As I said, these are amongst the easier versions. We're going to see some really, really interesting graphs come up on the next notes worksheet there. But for right now, let's go ahead and just take a look. So just kind of thinking here, let's do radian mode first and foremost. So radian mode on the calculator. And then as a matter of fact, let's go down to where it says FUNC for function, and we're going to change that. And so actually, I'm going to have you move over 2 to the right there, and there it is, everyone, POL. That would be polar form. And watch what happens when you hit the y equals on your calculator after you are now in polar form. So I go right there, and look what the variable is. The variable is r. So instead of y in terms of x, you'll see it's r in terms of theta. And as a matter of fact, everybody, I'm going to circle just one of the buttons on the calculator here. Does everyone see that as kind of our independent variable here? Remember, that was your x button. This is for something called parametric. But there, guys, go right over and you see for the polar, the one that matches up, there's your theta. So as a matter of fact, I'm just going to type that in and clear it, but there it is. There's your theta. So r in terms of theta. Now in this case, we just wanted to type in r as 2. And for most of these, I'm thinking the zoom trig window would work. So guys, hit zoom at the top if you get a chance and hit number 7. And there it is. This just happens to be exactly 2 units here and 2 units here the way the trig window is defined. And so there's your perfect circle. Excellent. In fact, I'm just going to square that up just to see it a little better. See? Yeah, not too bad. All right, good. Let's go ahead and do letter B, everyone. So theta equals pi over 4. Let's see what this would look like first and foremost. So find the infinite number of ordered pairs, or points I should say, that have theta being equal to pi over 4. Well, let's see. I'm just kind of thinking out loud with this. This is the terminal side right here with theta being pi over 4, right? That's 45 degrees. So any point on that terminal side, I'm just going to sort of do this, any point on that terminal side would be part of this. That would make it up. Also, here's what's kind of interesting about this, and I guess I would ask this to you. Is this a point where theta is equal to pi over 4? Is this a point where theta equals pi over 4? Is this a point where theta equals pi over 4? Well, theoretically, the answer would be yes. Because here is a point right here where I could make theta be pi over 4 and r be what type of number, everybody? Negative. So if I have a negative r, that would bring me here through the pole, puts me back up on pi over 4. So let me describe that a little better for you. So in this case, remember the issue is if theta is pi over 4, I would rotate here first, do theta first, but if r is negative, I would be moving through the pole down here. And so these points, theoretically, can have an ordered pair where theta is pi over 4. And so as a result, what you end up getting is not just a ray coming from the pole, but literally a line stretching to eternity. And there we go. There's your line right there. Now what would that be in rectangular form? You know this. You've seen this. In fact, you've seen this ever since Algebra 1. But let's go ahead and see if we can convert it together. So this one just requires a little trick, by the way, right here. So nothing really above. Well, I guess a little bit of the above will help us. How do I kind of work with theta, getting it into x and y? As you can see, the connection is all based on the tangent ratio. So this is what I'm going to use right here. It will be a little contrived, but this is the trick that works for this one. I'm going to take the tangent of the left-hand side and the tangent of the right-hand side. Kind of an odd algebraic step, but perfectly okay as long as I do something to both sides of the equation. Now remember, tangent of theta is something we've been looking at now for months. Tangent of theta is a ratio of the y to x. And now as you can see, what I've done is taken my polar form, in this case the theta, and changed it to y over x. And let's go one step further. You know your unit circle really, really well. What is tangent of pi over 4? And tangent of pi over 4 is exactly 1. And so what you end up getting is that piece right there. I would bring up the x, of course, and you end up getting y equals x. Think of this as a y equals mx plus b. Y equals 1x plus 0. And everybody take a look at this. Does this look like, first and foremost, it has a y-intercept right at the 0? Sure. And does it go up 1 over 1, up 1 over 1, up 1 over 1? Yeah, it certainly does. It's tough to grasp the theta equals on the calculator there, so I'll let that one go, and then we'll go ahead and do the others. Alrighty. So everyone, let's go ahead and just take a peek at this. Let's change gears a little. Let's do the conversion first, and then use the graphing calculator, kind of work it out that way. So anyway, x plus y equals 4. Now it's time to get really into the good algebra with this, is I need us to convert from rectangular form. And by the way, this is a line on the coordinate plane. I hope everybody realizes this. This is a linear equation. It looks like the y-intercept will be 4, and the slope seems to be -1 as I see it. But regardless, what I want to do is convert that to polar form. So let's get comfortable with the stuff up above. How do I change x to polar form? How do I change y to polar form? Well, everyone, here's how I change x nicely to polar form, and here's how I change y nicely to polar form. So again, just kind of get comfortable with recognizing that aspect of it, where if I see an x just kind of sitting by itself there, I know x is r cosine theta by definition. And now notice, rectangular, polar. Excellent. Now everyone, when I see a y just kind of hanging out by itself, there's a way to get that into r and theta. And that's the idea. You're changing from rectangular to polar. Sounds good. Now again, we're really just working on good algebra with this, not a whole lot more at this stage at least, but how would you get an r equals here? So think about some of the algebraic techniques that you've focused on for the last several years. What would be the way to get this down to a single r? I have an r in this term, and I have an r in this term. Well, I'm hoping that you focus a lot on that idea of factoring. It just comes up in so many different contexts that very simply, if you factor out that r from each of those two terms, I get that, and then I'm hoping you would see that that then divides on down, and lo and behold, I get this piece right here, cosine theta and sine theta. Notice, explicit form, r equals, all in terms of theta. Okay. Excellent. So this was rectangular form, and now this would be the explicit version of polar form. So 4, and then over cosine theta and sine theta. Let's get that going. Nice. Well, let's go ahead and just graph that quickly just to see. And kind of sketch it on the rectangular one, but just kind of get comfortable with this piece. As I said, these are very, very generic equations at this point. In fact, I'm more concerned about the algebra here than anything else. As I said, we're going to really open it up on the next notes worksheet and look at some really fascinating graphs that you can create in polar form that you're simply unable to do in rectangular form. Let me just make sure I have everything covered there. Yeah, it looks decent. And I'll just go ahead and hit graph at this stage. And there you go. Here's your y-intercept up at +4, or your intercept up here, and coming down here with the slope of -1. So it does look something like this. Let's go 1, 2, 3, 4. 1, 2, 3, 4. And looks something like that. Just a line on the coordinate plane like that. Again, just two different forms of the same graphical pattern. I would argue, obviously, that rectangular is easier to use than polar. And that's why you've been kind of working on that one ever since Algebra 1. Okay, how about this one? Nice parabola on the coordinate plane, rectangular. Let's go polar on this. So I'm going to write this just down here, start it out. And, we all know what this looks like. But let's go ahead and see it in polar. All right, everyone get comfortable with that piece. I just have a y on the left-hand side. When I see a y, it now becomes automatic, everyone, r sine theta. Now this one will be a touch careful on, but it looks like r, oops. In this case, we do want to write r cosine theta, and then squared. Excellent. This, everybody, is an exponential property we developed in Pre-Calc 1, the very beginning. Kind of looked at this as taking r squared and cosine squared. So that's what it would be right there. Remove those parentheses by taking each one squared. Sounds good. Now, the dilemma I see on this one, and let's see if we can find a way to remedy it, is I have an r on the left side. I have an r squared on the right side. In terms of them being factors, I think what we can do here, everybody, is divide both sides by r. That seems a pretty quick fix here because the r's would cancel here, which is a good way to do it. And remember, the only reason we can do this is because this is separated by multiplication. So a common factor, they can go. And then everybody, what is r squared over r? Well, I think that's still r and then cosine squared theta. So I'm seeing that as our ticket forward. And remember, the goal is to go ahead and get the r by itself. Well, now by doing that piece right here, I do just have this little factor of r right here that I can get by itself by bringing the cosine squared over to the other side. And so I think that's going to do it. We're going to check this, of course, momentarily. But I'm seeing this as sine of theta over cosine squared of theta. And if you plotted the infinite number of ordered pairs that make this equation true, it should be the same parabola as doing it in rectangular form. So two different versions, of course. Let's go ahead and take a peek on that. I'll bring this over for just a sec. So I go back, go to your r equals now, not your y equals, but your r equals. And let's type in sine of theta. Just be a little careful with some of these parentheses here. And then I'm going to do this cosine theta, and then square that. Something along those lines right there. Take a peek. And let's just see if this works. Should get a decent looking parabola out of this. I'm going to hit graph. And there we go. Looking pretty nice. Vertex at the pole, and parabola shooting upward from there. So it doesn't have to be perfect by any means, but let's go ahead and sketch that in. Something like this would do. I'm not asking you to point plot or anything like that, just understanding sort of the nature of the two different forms. All right. Good. So it looks like those two, everybody, were rectangular to polar. And I like that piece, just turning an x to r cosine theta, turning a y to r sine theta. That works out fairly well. Okay, let's do this one right here, and it just depends how far we want to go with this one. So E and F, let's reverse course here, everyone. So r equals 2 cosine theta. And we'll go ahead and take a look at this on the calculator in just a little bit, but for right now, let's go ahead and convert. Now, remember the scenario at hand here, everybody. We want to go now from r's and thetas to, sorry, just give me a sec, to x's and y's. Now, here's the thing that I see. I saw a cosine theta in that on the right-hand side. The only thing that was missing that would really make sense is if there's an r there. So cosine theta by itself doesn't do anything for us. But r cosine theta, by definition, everybody, is x. So in terms of a technique to move us forward here, here's what we're going to do. And actually, it's almost like two birds, one stone. Because take a look, everyone. If I go ahead and multiply the right-hand side by r, because that would be great. Instead of 2 cosine theta, I would love a 2 times r times cosine theta. Well, I can do that. I can multiply that right-hand side by r and tuck that in there. Now this, everybody, is something we can work with. What's obviously the only thing I need to do to make sure this is legitimate? Obviously, everyone, I have to multiply the other side by r. And so that, I believe, is our technique right here, by making sure we get not just a cosine theta, but an r cosine theta. And I can do that as long as everything's in balance. Now, as I said, this works out quite nicely. The right-hand side now speaks for itself. R cosine theta, by definition, is x. Please keep that in mind. That's great. And this is something we know that converts directly to rectangular form as well. X squared plus y squared. Now, theoretically, what I would encourage us to do is bring this over. If you stopped right here, it's not the end of the world. I mean, you've done your job, right? Isn't this all in x's and y's as opposed to r's and thetas? Yeah, sure. So this is it's a good answer. It is. I'm going to encourage us to maybe go a little further here. So if you don't mind kind of watching here as we go through, do you remember, and by the way, this forms a circle on the coordinate plane, just so you know. That should look familiar with just your x squared and your y squared. So basically, I'm going to bring the 2x over. And if you remember the form from way back when in Pre-Calc 1, it works really well in what is called completed square form. So I'm going to just go ahead and complete the square here. You can kind of take a look with me. Anyone happen to remember just how do I complete the square right here? What am I going to add on the left-hand side? Well, take this and divide by 2. So that would bring us down to -1, and square -1, and I get 1. And so I end up getting this piece right here. And as a matter of fact, this would be x minus 1 squared plus y squared, and then equals 1. That would be a great answer for this one as I'm looking at it. I'm going to go with that. As I said, if you stopped a step or two short of that, I can live with it. It's not that big of a deal. And you know what this means, as a matter of fact? Again, not that you would remember. I'm going to graph this momentarily on the polar calculator in just a sec. But this has, if you remember correctly, a center of 1, 0. So here would be your center. And this is r squared, everybody. And actually, r is also 1. So this has a center of 1, 0 and a radius of 1 unit. So it should look something like this right here. Again, this, a lot of the conic sections, the polars really are just quite a bit easier to work with. So let's go ahead and see that in polar form. So nice and straightforward. Watch how easy this is to type in. And if I, again, put the infinite number of pairs that make that equation true onto the polar coordinate plane, I should end up getting here. Let's go ahead and do it. There it is. This is your 1, 0 right here, because remember that's pi over 2. So I put this on the trig window. But there we go. Just there's your 1, 0 and a radius of 1. So here it would look something like this. And there's your center. And not too bad. Excellent. All right, everyone, just one more, and then we'll wrap this on up here. This is a tough one. Let's see if we can make it work here. So I have r, and then 4, 1 plus sine of theta. Everybody, it would be great for you to do it on this one is pause the video. See if you can do this intuitively. And if not, as I said, this is among the hardest ones, at least for this particular lesson. So, but try it. Try pausing the lesson, see what happens there. Okay. Well, let's maybe see how you did. The first thing I saw, just in terms of looking at this equation, is this denominator. There's nothing really down here that I can do. I brought it on up, and actually I kind of like that because I'm going to create a couple things that I'm going to need here. So I did that when I looked at this one. And then remember, sine of theta is really a no-go. But r sine of theta, we're right there. So by distributing this in, I get at least something that I can work with quite well. So I get that. That looks great. Now, again, from what I see, everybody, this is taken care of. That's a no-brainer. Everybody, r sine of theta is just y. Now this one right here, it's going to get a little ugly, I guess, but I think it can still work. We do know how to translate just a standard r, not an r squared, but we do know how to translate a standard r into x and y. Here it is. Again, it's not ideal. I would agree with everybody on that piece. But r is this, using Pythagorean theorem. So I'm seeing this, everybody, as this piece, x squared and y squared. All right. Now, theoretically, as I said, I've kind of done my job. This is as ugly as it gets, but notice I've changed it all. Here we started in r and theta. Here, everybody, at this point, I'm in x's and y's. I'm in rectangular form. But I think we can do a little better on this. So here's how it does play out. Bring over the y. And you don't see too many rectangular equations with this massive square root right here. So any ideas on how we're going to get rid of that square root? Let's square both sides. I'm going to bring this on up over here, everyone. Now the good news is that whole side right there, that is x squared plus y squared. Okay, so the left-hand side, that big quantity, that big root goes away. And so I'm left with the quantity x squared plus y squared. Now careful on the right-hand side. I've seen students do this many times over the years. You do have to be a touch careful. Remember, this is not just 4 squared and y squared. This is 4 minus y times 4 minus y. So you would have to FOIL this, everybody. And I don't mind foiling it out for you. I end up getting, if I FOIL, I get a 16. I believe I get a minus 8y and plus y squared. I think that's what happens when you FOIL that piece. Okay, sounds good. I think we're just about there. Let's go ahead and put this together. Do you happen to see anything? To me, something is jumping off the board at me in terms of simplifying this. If you look, I have a y squared on the left, and I have a y squared on the right. If I basically subtract y squared on both sides, do you see that those would cancel? And so that's even a little cleaner, not bad at all. And again, I'm getting better and better at this. I would maybe ask us to go half a step further. And what do you say we solve for y here? Again, not the end of the world if we don't. I like that answer right there, by the way. But I would put it in more explicit form, solve for y. So guys, just to wrap this on up here, I would subtract 16. And then how about divide by negative 8? Yeah, I kind of like that. Probably a couple different ways to express it even from there. But I'm going to leave it and go with it. Ooh, I forgot to put my y equals. That was random. There we go. So x squared minus 16 over the negative 8. Hey, why don't we take a quick peek? Oh, and by the way, any ideas what this would form on the coordinate plane? You've got a y, and now you have an x squared over here. Yeah, it looks like a parabola to me. Let's just quickly see it and wrap this on up for you. Bring this on up. So what the heck is this one? There we go. So I go right here, and 4 divided by, and I'm getting a 1 plus sine of theta. And let's take a peek. There it is. A nice wide parabola there. Looks like up here, starting at 2, and something like this would do. Okay, so as I mentioned, really just some of the basic polar equations here today. Converting from one form to the other. Everybody get some practice on that piece. And what we'll do on the next notes worksheet is take some time and investigate some of the more complicated, complex, and really visually intriguing graphs. There's some really amazing patterns that you can create in polar form that you simply cannot do in rectangular form. So it does have sort of an added benefit there. Anyway, if you have questions, let me know. And of course, thank you for listening.